linear regression. And in order to start with linear regression, we are going to continue with the example that we discussed last week for a while, which is this example in which we had collected data on the relationship between how much budget was invested in advertisement on the radio, newspaper, and TV, and how much this influenced our target variable, which was the sales, the overall sales. So you can recall some of the plots that we have here, where basically, I think you can see my mouse when I move it, where basically you can see how the different data, which are these orange dots, relate the investment in the TV, for example, with the sales, the same for the radio and for the newspaper. And basically what we have done is that for each of these pairs, you can also see this blue line, which is a linear approximation of how the investment on the TV influences the sales, and the same with the radio and the newspapers versus the sales. And in particular, this blue line that we got here is actually the result of the least square linear regression, which is going to be the main topic of today's lecture. So some of the questions that we are going to address in the lecture of today are the ones that I present here, where first of all, we are interested in seeing what is the relationship between how much we invest in advertisement versus the sales that we are going to have after that advertisement, whether this relationship is strong, and by strong in general, we are going to talk about statistically significant, and which media are going to be the key ones where if we invest, they are going to contribute to increase the sales. As we were seeing in the previous slide, that is, the more we invest, the higher the sales look. Of course, we are going to be fitting this least square linear regression, and this is going to have some parameters. The linear regression, the least square linear regression is a parametric model. And one of the main questions that we might want to address is actually how good our estimation of such parameters is. And what is the effect, or how well our predictions, if we now have a new observation of the budget that we spend in advertisement, how well we can predict the sales of the future, so that maybe we can plan ahead on how we invest this budget in order to increase our sales. And of course, up to this point, I mean point 6 of this slide, we are going to have been assuming that the relationship between the budgets that we invest and the sales is all linear, but this is just a modeling assumption. Of course, we might also wonder whether this is the case or not. So simply moving forward, if I manage to send a slide. So in general, in a simple linear regression, this is the first part that we are going to consider. We are going to consider only one input variable, which univariate input variable, which we are going to denote here by X. This is our target variable. This is what we were talking last week. And then we are going to assume that in the underlying true data generation, actually the relationship between our budget and the sales is going to be linear. And it's going to be linear with some given parameters, beta 0 and beta 1, which if there is no hat or tilde on the top of them, I'm going to assume that they are the right one. And this is only up to some approximation level, because in general, as you may recall from last week, usually there is an additive noise term that we usually consider here, right? So we don't assume that the sales that you are going to have is deterministic given the budget, but there might be some level of noise, some level of stochasticity that may happen just because usually the relationship between these two variables is not deterministic, so that we treat them as random, at least the y. So we are gonna say that we regress on Y onto X, and we are gonna say, okay, I observe a set of realizations for the budget of the TV, and I also, together with the sales that they incur, and our main objective is, under the assumption that this relationship is linear, right? I'm gonna use the data that I got, which I'm gonna call training data, to estimate this beta 0 and beta 1. And with these estimators of beta 0 and beta 1 is what I'm gonna call this beta hat 0 and beta 1 0. And what I'm gonna do is that, given a particular realization of X, so how much I invested on TV, I'm gonna have a predictions on the sales. So as I was mentioning, we are gonna assume overall the talk today that our training data is gonna consist of n observation, where each observation is not gonna be anything else than one of these pairs I was commenting before, which has a particular observation on the budget, for example, on TV, and the sales that I collected, and we have n of them. I believe, if I don't remember wrong, that in our data set there were 200 samples of this sort. And as I was saying, the goal is gonna get to be good estimators of V0 and beta, of beta 0 and beta 1, which I'm gonna call beta 0 and beta 1 hat. And this is gonna allow us to see how well we fit the data that we are given, this training data, but also our main goal is also gonna be to see whether I can make accurate prediction for future unseen data, and by unseen data, I mean new X's. So moving forward, in order to estimate these coefficients, basically we are gonna need to set a loss function. And this loss function, as we anticipated already in the previous lecture, is gonna be the least square. And the least square is not gonna be anything else than the sum of the squares of the errors that we commit between our true or target variable in the training data and our prediction for all the data sets. So basically, our loss function is gonna be what it is also called the residual sum of the squares, where basically for every observation in the training data, we are gonna measure this error, we are gonna square it and sum it up all over the whole training data set. If we write down how our predictor is, which is no more than the beta 0 hat plus beta 1 hat multiplied by x1 to the square, we can write the residual sum of the squares as shown here in this expression. And this is a quadratic function in beta 0 and beta 1. So that whenever we want to minimize, of course, we want to minimize this error, and we know that it is quadratic in beta 0 and beta 1, so it's going to be of this shape. We know that if we take the derivative of this function with respect to one of the parameters and make it equal to 0, and then try to find the value of beta 0, for example, if I take first the derivative of beta 0 of this sum of residuals, square residuals, and make it equal to 0, I can obtain a beta 1, which is gonna be a minimum of this convex function. So that I'm gonna make sure that actually by simply taking the derivative and making it equal to 0, I'm gonna be able to find the parameters that minimize this RSS. And actually, if you do so, if you take this loss function and take the derivatives and make it equal to 0, what you get for the least square estimates of the parameters are exactly what we saw here in red, which if we start with beta 1, I recall that beta 1 is the parameter that multiplies the input variable x1. Basically, what we have is a sum over overall data set where we compare the value that we observe for the variable. So the budget that we put in one particular observation on the TV advertisement minus the empirical mean of the x's multiplied by the difference between the output variable that we observe for this particular observation minus the empirical mean of the output variable. And when I say this x bar and y bar as empirical means, I just mean to take the empirical expectation or empirical average given in the data set. So basically you have on the right side, bottom right side, you have their values where basically you take what I just also sometimes call the Monte Carlo estimate of the mean, which is 1 over n, and because n are the number of samples, and then you basically take the sum of all these and you get the empirical mean. And you can do the same with the x's. Remember that we are now in the univariate input variable. And basically what we get is this in the numerator, and in the denominator we have simply the difference between the x's, the input variables, minus its empirical mean to the square. This is for beta 1, and it is quite easy to show that if I take the derivative of this loss function and with respect to beta 1 and make it equal to 0, I get it here. And the same with beta 0, I can do the same. And if I do a bit of math and get the beta 1, I can show that beta 0 is no more than the empirical mean of the y minus beta 1 multiplied by the empirical mean of the input. And something that it is important here to notice is that if the empirical mean of your input variables is 0, right? Basically, the beta 0 is not going to be anything else than the empirical mean of your output variables. Okay, so to give you an example, if we do the least square estimator, assuming a linear regression with a least square loss function, or the residual sum of squares, and we have the TV versus the sales, in our least square estimators for beta 0 are going to be 0.3 in this particular case, and this small value of beta 1. And this is one example. Let me see if I can move. And the question is that so far we have done this estimate of how the TV's budget and the sales relate to each other. But the main question, one of the main questions that may arise is actually how accurate the coefficients are. Because I was saying that initially I'm assuming that actually the true relationship between x and y is linear, of the form that I have here in this first expression. And now I have some estimates for beta 0 and beta 1, which I estimated given the data. And the first question that I may have is that how accurate or how close our estimations of beta 0 and beta 1 are to the true values, under the assumption that the actual relationship is linear. And of course, that is going to depend on how many data I have. That is first of all, and we are going to see that in a second. So if we basically think of running a least square estimation or least square regression, and we would do it at the true or at the population level. By population level, I mean by keeping in mind the whole distribution of x1, what we would get is actually the red line here. But by only observing a subset of the data, which are these gray circles, what I would get is instead the linear model in blue. And as you can see, they differ with each other because basically everything I was given was not the whole distribution of x1 or x in this particular case, but I was given only with some samples of x and y and how they relate. And if instead of having this particular realization of x and y's, this subset, I would have another one. It might be that my linear or my linear estimator, my linear regression would be different, right? I would get different estimates because as we saw in the previous slides, 2 slides before, here basically I depend on the particular values on the variables in my training set. So if I change my training set, my estimators will change. So the question is, how well this estimator that I got generalized to the whole population, right? So if I would get now samples which are different from the ones on the training data set, would I still be doing a good fitting? And this depends, of course, on the size of the training data sets, which in general always is going to be finite. So you never get the whole population, which would be an infinite number of samples, but what you get is a finite sample. And in this particular right side example, what now we saw is that in these very light blue colors are the variability that you get when you collect different data sets, right? So every data set is gonna give you a different linear regressor, while the true one is the red one I'm showing here. So the question is, as we were seeing before, whenever we estimate the mean of a variable given some realization, some samples of that random variable, we can do what I call the Monte Carlo estimate, which is an empirical estimator of this target value by simply taking the average of the samples that you were given. And we have seen that to estimate the empirical mean of X and the empirical mean of Y. And in general, what we know is that this estimator I just saw here is an unbiased estimator of the target variable, which is actually the mean of this random variable. So this is the case in general, whenever you want to estimate the average value of any random variable, but this also applies to the least square fit. So what we are going to see is that the least square fit is an unbiased estimate of for the population regression line. And importantly, and as you will be playing around in your first assignment, if you have had a look already to that, what we can actually show is that the least square estimation of your parameters, which is of the form that we saw a couple of slides before, is not only an unbiased estimator of the true parameters under a linear relationship of X and Y, but also it is an estimator that shows the smallest variance across all potential unbiased estimators. So this is in general going to be a very nice property because you don't only get an estimator which is unbiased, but also you get an estimator which has the smallest variance, meaning that it doesn't matter the variance of the values that you are going to get, how much the values of your estimators are going to change across different training data sets is going to be minimal. Of course, it will depend still on the size of your training data set, but still you cannot do better given a current sample size. So in that context, the question remained the same. So how accurate is the estimator, what we call hat, mu hat of mu? And in order to evaluate that, in general, what we are going to measure is what it is called the standard error. And the standard error is nothing more than the square root of the variance of the estimator. And in our particular case, for this linear regression, the variance of the estimator is the actual variance of the output variable. Remember that we were assuming that y was equal to the f of x function plus some epsilon, and this epsilon, which was noise with zero mean, had a variance sigma. So here what we are going to have is the sigma squared over n. And of course, as I was mentioning before, sigma is no more than the standard deviation of the population in Y, and n is the sample size of our training data set, how many observations we collected there. And what it is very important to assume here is that we recall that up to here and in general in most of the course, what we are going to assume is that this error is going to be independent on X, right? We are going to assume that X and epsilon are uncorrelated. So basically every time we get a Y, it is going to be an IID sample or the noise of the Y is going to be an IID sample of whatever distribution of this epsilon but that means that basically our sigma, our error noise variable, is gonna be equally distributed across all the observations that we got. So something that it is also important to observe in the standard error is that this sigma here, it is constant, and remember that this had to do with what we call before the irreducible error in the previous approach. But in general, what we are gonna have is that the more observations we have, the smaller the standard error of our estimator. So if we recall here that we have these 10 least squares, basically you can see that still, even if we have like 10 different data sets and there is some discrepancies between the different regressors that we get, they basically don't go very far away. So we don't get any lines anywhere very far away from the true value. And they are all somehow around the true population regression line. So in this discussion on the standard error was in general for any estimator mu hat of mu, but of course, if we come back to the linear regression that we are working today, what we can do is to compute the standard error for both of the parameters that we are trying to estimate, this bias parameter, beta 0, and this beta 1 parameter that relates x with y. And what we can show is that actually this standard error, in the case of beta 0, is going to depend on the population standard deviation, or the variance in this particular case, because it has the square, and then it has a sum where the first term is 1 over n. So as we increase n, this term is going to go to 0, and a second term that basically depends on the empirical mean of our observations divided by how far every sample is from x bar, which is the empirical mean of the x's. Of course, if my data are shifted or pre-normalized in a way that this x hat is equal to 0, these terms disappears, and basically what we get is something similar to the case that we were showing in the case of mu on the left side. If we look then at the standard error of the beta 1 of the second parameter at the square of it, what we get is basically that we get the variance of the population, and then in the denominator we basically has the deviation of every sample with respect to its empirical mean. And here again, this sigma, in our particular case, assuming that the true relationship between x and y is actually linear, what we have is that sigma squared is the variance of the additive error that we were having. The problem that we may have here, of course, is that if I don't know fx and I only see x and y, we don't know what epsilon is, and we are not going to know what this epsilon is in real data. We are not given with the epsilon. We never get separated the y and the epsilon. We only get to see y. So if I manage to move away, so we are gonna see that since this is unknown, what we are gonna need is to get an estimate, a sample estimate from it. And actually, the sample estimate of the deviation, the standard deviation here in 0.3, right? We can do it by taking simply the square root of the sum of the residual squares divided by n minus 2. And this is going to be an estimator of this sigma, because remember that the sigma is unknown, but we can come up with this estimator, this standard error this estimator of the deviation, standard deviation, which is no more than the residual standard error. And as in terms of the standard errors of both of the estimators, basically here you have some of the relationship that we commented before, that basically if x, the empirical mean is 0, then basically beta 0 is going to be simply the empirical mean of y. Again, remember always that this only occurs, or we can only do that in case that all the errors are uncorrelated. So there is no correlation between the X and the error that we commit. So far, we got to see how good this, or we got to see what is the standard error that every of the parameters may commit, but something that we haven't yet measured is how off our particular estimator is going to be with respect to the ground truth parameter. And in order for that, to measure that, what we can actually measure are, or compute, are what they are called the confidence intervals. So for example, a 95% confidence interval are gonna tell you that basically the parameters, the true value of betas, is gonna be in the interval with 95% probability. And in the particular case of linear regression coefficients, this the confidence interval, or the 95% confidence interval, can be computed as our least square estimator plus minus 2 times the standard error that we just computed in the previous slide. And this is not only gonna give us a point estimate of beta 1 and beta 0, we got the 2 in here, but it is gonna also tell us with 95% probability how far the true values can deviate from the estimate that we just got. So why this is the case? Well, this is the case because in this particular example, and because we are using the least square loss function, we are actually assuming that the error in the output is Gaussian distributed. And the coefficient estimates that we are actually getting in turn are going to be also Gaussianly distributed. So basically, when we look at here, when we move away by 2 standard deviations from the mean of a Gaussian, basically we have covered from between minus 2 sigma and 2 sigma, we have covered 95% of the mass of the PDF. So if I take an integral from minus 2 sigma to 2 sigma, I basically have already gotten 95% of the probability of the overall variable. Sorry. So in that regard, under all these assumptions where the noise is independent with this variance, we have used the least square. We can assume that the error is going to be Gaussian, and then we can easily compute these confidence intervals using the standard error that we computed before, and say, okay, with 90% probability, our true parameters are going to be in between these two values as I computed here. So coming back to our previous example, while initially when I showed you this plot with the TV and the sales, we were only having beta, the particular value of beta 0 hat and beta 1 hat, which were point estimates. And we had these values of 7.03 and 0.04. Now, what the information that we are adding on the top of that is that we know that with 90% confidence or probability, actually, beta 0 is not going to go below 6.1 or above 6.9. And the same we can do for beta 1, where we know that beta 1 is not going to go below 0.042 and 0.053 as an upper bound with 90% probability. So that simply means that even if we collect another data set, we expect with 90% probability that if we train again a logistic regression, probably the values are going to be there of the same sample, but also the true underlying parameters are also going to belong or be with 95% probability in this interval. Okay, so all the way here, everything clear? Any particular question before I move towards hypothesis testing? It seems we are all good. Okay, awesome. So far, we have made the estimations of our parameters beta 0 and beta 1, and we have also computed some confidence intervals that tell us how good these estimations are. Of course, the smaller the confidence interval, the more certain we are aware about our parameter estimation, and the wider these confidence intervals, the more uncertain we are. Right? And then the next question that we might wonder, which answers the second question, is actually, is there any information in the budget that I invest in TV when predicting the sales? So there is a statistical significance that tells us that if I invest more money into TV advertisement, I will actually increase the sales? Or this was simply by random chance? Right? And in order to do so, what we are gonna do is a hypothesis testing, where in general, we are gonna call the null hypothesis the one which is the simplest, where, for example, in our case, we are gonna assume that there is no relationship between the budget that I put on the TV and the sales, versus the alternative hypothesis, which is the one that we are usually interested about, which is there is a relationship between X and Y. So in our case, how this null hypothesis and alternative hypothesis translate into a particular form is that the null hypothesis is going to assume that the beta 1, the parameter in the linear regression that multiplies x1 towards the output, is going to be 0, and the alternative hypothesis is that this is not the case, but this is different than 0. So it has either a positive or negative correlation, while beta 1, 0 means 0 correlation between TV budget and sales. And in general, what we are going to try to qualitative evaluate is whether beta 1 is far enough from 0 so that actually our relationship is not just chance, but actually there is a statistically significant correlation between the TV budget and the output variable. And the question here is that, of course, what that means to be far enough. And this, since we don't get beta 1, remember that we never get to see the true parameters, what we are gonna need to look at is actually our estimate of beta 1, which is beta hat 1. And we are gonna try to measure the relationship between TV budget and sales, not by the true parameter beta, but actually by our estimator. In order to do so, what we are gonna do is that what we can do is the T statistics will actually normalize the deviation between the estimators of the two hypotheses. So basically, remember that the alternative hypothesis is beta hat 1, which is our least square estimator, and the null hypothesis in our case would be that beta 1 is 0. And then we divide that by our standard error on the estimator, because this is also telling us how certain we are about the value that we estimated, right? And this T is also often called the seed score. And basically what the T statistics, they are called T statistics, basically what they have is a bell shape that, depending on what the value of T is, you basically get a shape of the one that we saw before. And this bell shape, as we have a number of samples in our training data, which is larger than 30, usually the bell shape that we obtain is very similar to the bell shape of a Gaussian. And we know how to, because we saw that in the previous slides. Here, this is a Gaussian and this is a bell shape. Just for those that are not familiar, the good thing is that we know how much probability mass goes into the different regions. So you can see that basically almost 70% of the probability goes into 2 standard deviations, from -1 standard deviation to +1, and already 95% goes in between minus 2 standard deviations to 2 standard deviations. So the fact that this actually has a whenever we have enough data or data greater than 30, this has a shape of similar to a Gaussian, allow us to get these probabilities quite easily. While in other distributions, getting this integral that we want to take is not as easy. So that is simply the main advantage. Yeah, so I had it here. I have forgotten. So basically, what we can do is that whenever we have a t-statistic, what we are going to get is a value, and if the absolute value of t, because remember that we can go away from the mean of the bell towards the right, but also towards the left. Basically, if we want to go to a value which is greater than 2 standard deviations, so we are in this region, orange regions, either on the right or on the left, basically the probability of this happening in this particular case is 5%. And this probability, the probability that you go beyond that value, it is what we are going to call p-value. Simply you take the value of t, you see where it falls in this x-axis, and then you see in which range of probability you are. So if your t falls into the orange area, you know that the probability of falling there is smaller or equal to 5%. If you fall into the yellow area, the probability is roughly 26-7%. And if you fall into the green area, you have quite some substantial probability. So basically, as I was saying before, if the p-value is very small, it is quite unlikely that the observed association between the input and the output is due to chance. So for a p-value of 5%, that would simply mean that only 5% of randomly chosen training data sets would have fall in that area. And 5% probability is quite a low probability because, I mean, there are a lot of training data that you could have sampled. And in that particular case, what you can tell is that we reject the null hypothesis at the significant level of the p-value. What does it mean to reject the null hypothesis? Basically, that the relationship that we observed in our training data set between X and Y was by random chance. And if we can reject that, what we can say is that we have a statistical significance saying that this relationship is not by random chance. It's not because we got a random data set where this might just happen by chance, but this relationship may occur on other data sets. Some typical values for the p-value are, to reject the null hypothesis, are 5 or 1%. Of course, as I get smaller with the p-value, I become more restrictive. So I become more harsher in order to reject the null hypothesis. You can go arbitrarily small, but of course, depending on how your data set is, it might be hard to go into very small values because there is a lot of uncertainty because your data set was too small. But in general, values of 5%, 1% are usually good. And in terms of n equal 30, where with a data set of observation n equal 30, usually you get these values by the bell shape that we got on the left side on this Gaussian distribution. So if we now look at the t-statistics and the p-values that we got in our linear regression model of the TV budget versus the outcome variable, the sales, these are the coefficients that we got at the beginning. These are the standard errors that we computed a few slides before. And now we got t-statistics, which are of the value of 15 and 17, which, as you can see, are quite far away from 0, and also assuming that you have this value and this statistical error, they are like quite far away from the mean value. And that means that the p-value is actually smaller than 0.0001. So you are quite certain that both of these parameters are not by random chance, but you are quite certain that they are doing their job. So that means that, for example, in the case of TV, that the probability that the relationship between TV and the sales that you observe in the training data set is by random chance is smaller than this very tiny value that you got here. I see a rising hand. Is that a question?
Yeah. Weren't we talking about values, p-values between 5 and 1% in the previous slide? Why is there such a low value of p in this slide, or am I misunderstanding something?
So basically the values that I mentioned before are the thresholds that you usually put to accept or reject the null hypothesis. So if you go below 0.5%, if you go below 0% in the probability that in the p-value, you usually reject the null hypothesis. And in this particular case, what we were obtaining are these p-values, which are way below either 1 or 5%. So we are quite certain about rejecting the null hypothesis. But usually this is hypothesis testing. So you say, do I reject hypothesis 0 or not? And usually this 1% is the threshold that you are gonna put in order to reject the null hypothesis. Clear? Good, awesome. So this was with the case of the TV, but remember that what we could do in the same way as we did fit a linear regression between the sales and the TV, we can do a similar work with the radio. Instead of looking at the TV budget, we just now look at the radio budget and fit a unidimensional linear regression. And what we observe is that we obtain different coefficients and standard errors, but still our statistics here are quite high, and the p-values are also of a very small order of magnitude. So we don't have any statistical evidence to claim that the relationship between the radio investment and the sales is by random chance in our data set, but we are quite confident that even if we would have taken another training data set, that would remain the case. And the same happened with the newspaper. Basically, the values on the table change, but they all have very small p-values. So now we have said, okay, how well I estimated my parameters. The second was, is the relationship that my parameters are indicated by random chance, or do I have any statistical significance that this is not the case? And the next question that we might want to ask is whether the model that we train is useful, is actually fitting properly the data. And in order to check how well we are fitting the data, and by fitting the data, I mean how well we are explaining our target or output variable, the first thing that we could, for example, measure is what it is called the residual standard error. And this is no more than the absolute measure of error of the model between the y's, the true target variable, and our estimations. And the residual standard error basically is computed as I saw here, which is no more than the 1 over n over 2 of the residual sum of squares. And this is simply to remember that that was simply an unbiased estimator of the variance of the noise that it is underlying the true data. And if we split that, this was simply how our estimated predictions compared to the actual values that we observe in the training data set, and we take the square. So in the advertising data, we were getting a value of 3.26. I guess this is for the TV. And since the mean of the sales is around 14, I think it was 14K, the percentage error is 20%. because basically you commit a 3.26 error out of an average value of y of 14, and then you say that this is 23% error. This is a way of showing it. Another alternative in order to measure the model quality in terms of predicting or estimating y, it is the R-square statistic, which basically explains the proportion of variance of the output explained by the input. You remember that whenever I was plotting the TV budget versus y, we had a lot of circles that were spreading not only on the x-axis, but even for very close values in the x-axis, there were quite some variability. And the question that we want to answer is how much of the variance that we got, how much of this sparse cloud of points that we got, have we explained? And for that, we can compute the S-square statistic, where basically depends on the residual sum of a square, the RSS that we computed before. It is right down here on the left, and the TSS, which is the total sum of squares, which basically computes how much each of the y values that we observe in our training data deviate from the empirical mean of the y. Just to give an intuition of what the TSS and the RSS mean in this context, basically the TSS measures the total variance in y, so how much you vary with respect to your actual mean of the variable, and the RSS actually measures the amount of variance that was unaccounted after the regression. Why unaccounted after the regression? The regression, that is no more than because we are measuring the square error between our prediction and the actual value of y. So the error, what we didn't account for. And if you look at this in that particular way, where basically we have 1 minus the residuals over the total sum of squares, right? It is quite easy to see that the higher the R-square statistic, the more accurate the model, because there is a minus aquí. And important to show that the R-square is in between 0 and 1. There is no bound for the RSE, but it is on the order of magnitude of y. That is clear because it only depends here, but this statistic is normalized and it is between 0 and 1. Still, while it might look a bit more interpretable, what is a good actual value of the R-square is something that it is not that clear. Do I need to be close to 1, or it is close to 1 too ambitious? And I think we are going to discuss this in a second, but something that maybe we should comment is that actually in the case of univariate case, the R-square statistic actually corresponds with the correlation or with the square of the correlation between your input and your output. And this quite makes sense because we are doing linear regression, so we are measuring linear statistical dependencies, and the R-square of this form, if you develop a bit more, you can actually show that the R-square is equal to the correlation to the square. This is simply playing a bit with the two definitions. I would recommend you to play around with that. This is not, I don't recall that it is in the assignments, but it is a nice exercise that you could do by yourself if you want to explore further. This is the case when, as I was saying, we are in the univariate case. So there is only one dimensional x, one x, but doesn't extend to the multivariate case. So the R-square statistic is not going to correspond to the correlation between x and y whenever we have more than one input variable. And we are going to see that whenever we move to the multivariate case. So this is basically what I have so far for univariate linear regression. But of course, I have been talking about sales, but I have been talking about investment in TV and in radio and newspaper. And so far I have only fit an independent linear model with one dimension between X and Y, or TV and sales, or radio and sales, or newspapers and sales. But why not to use all the information jointly and train a unique linear model with multivariate input? But I guess before I have a question.
Yes, I have a question about the slides with the examples on hypothesis testing. Mm-hmm. The data between the three media is quite variable, and the estimates for beta 1 also get worse, like the t-statistics get lower, but the intercept remains quite robust. Why is that?
What is quite robust? Can you?
So the t-statistic for the intercept remains quite high, even though the data gets much more variable, as we can see in the plots.
Yeah. So how to say? I mean, the three of them, as you can see, the TV has the highest slope, right? Compared to the other two, where, for example, the newspaper seems to have the lower slope. So there is clearly how big the slope is going to be is something that the beta 1 is telling you. So the higher the slope, the higher the beta 1. But that doesn't have to directly do anything on how well this relationship is, or how statistically significant it is. It might be a mild correlation, but still it can be statistically significant. That simply means that this correlation exists, and even if it is not very, very high correlation, it exists, and it is not by random chance that you estimated such correlation. Is it more clear now?
Right, I see that, but the t-statistics gets lower for newspapers, of course. It's still significant, but it's a lower number. But for the intercepts, the numbers remain very high, even though the data is
but
worse.
you need to understand that the actual value of the t-statistic by itself is not really telling you much. I mean, it is simply telling you that it is three standard deviations away, which is already a lot of the probability. The rest, if you go to 19, basically you are almost in zero probability, but basically you are on the tails of these Gaussian. So the tails of this Gaussian goes all the way to infinite, but up to some point, basically everything is almost zero. So once you have crossed the 2 standard deviations, or even the 3 standard deviations, basically almost no probability remains there. The problem is when you stay in the green area, and also a bit in the yellow area.
Okay, thank you.
Okay, so any more questions, and can I move to the multivariate linear regression?
Maybe another question following up to that. And it is also for the intercept that we saw. What exactly is the null hypothesis for the intercept? So is it also like null hypothesis is that it is zero, and alternative hypothesis is that it's not zero? Because we just talked about the beta 1 all the time, but never about the intercept.
Yeah, I guess the thing is that in this particular case, you need to recall that basically your beta 0 depends on beta 1, right? You see it here, that beta 0 depends on beta 1. So basically you can have you are gonna have a different beta 0 when there is beta 1 and when there is not. And therefore you can have this statistical test when there is beta 1 in place and when there is beta 0, or when there is no beta 1 in place. It is not that you remove or add the beta 0, because the beta 0 is assuming a constant. It is more how the actual value that you obtain of beta 0 when you consider also to have a beta 1 changes with respect to the other model. Clear?
Well, maybe I can reframe my question a little. So what does the t's or the p-value tell us? So because when for the beta one, it says like if it's like big enough, it says, well, it's probably by chance that we got like some kind of slope. But what does it tell us like accordingly for the intercept? What is the claim that you can make by the p-value?
I would say it's simply telling you, I mean, in general, I would only look at myself. I would mostly look at the p-value of the TV, but it is telling you, it is also telling you how much of by chance you got this actual linear regression, right? So if you would change to a different data set, you would get as kind of similar model. But it is true that the interpretation, it is with respect to the hypothesis testing doesn't make that much of an intuition anymore. But if you, because beta zero is simply a kind of a baseline, so there is no random variable associated there, but you can still measure the p-value by comparing the two models, the beta zero that you would get without beta one and with beta one, and still compute that p-value, but the interpretation is definitely not the same as you would get when thinking of beta one.
Okay, thank you.
Okay, so here we are. So coming now to the multiple or multivariate linear regression, what we are gonna now consider are the settings where instead of fitting an independent linear regression for every input variable that we had, we are gonna train a linear regressor where basically we have as many terms as input variables. So in our particular example, basically we will be making the assumption that the sales depend linearly of all of the three budgets that we had, which are the TV, the radio, and the newspaper. And in addition to that, of course, we have a bias term, which is the beta zero, which is the same as before. And we have our noise variable, because this is the main assumption that we are making, is that this relationship is linear and there is an underlying true set of parameters that we don't know, but they should be there. And if we do this same exact assumption as we were doing before, but now with multiple inputs, what we can now do is to actually minimize the residual sum of squares as we were doing before. And of course, what we can do now is to write this in terms of vectorial or matrix form, where basically now X is a matrix of size n times the number of input variables plus one, because usually we incorporate the beta zero also there. You can assume that there is an additional X, which is all equal ones. And then beta becomes a vector with as many dimensions as the number of beta zero all the way to p, so p plus one. So someone is writing in my, okay. Is there anybody that has a question? No, okay. So in this particular case, we can write the residual sum of a square in this vectorial form, where y again here is a vector, and we can find the least square parameters by taking the derivative with respect to beta and making it equal to 0 as we were doing before, but now we do everything in once. And basically, differentiating in this case with respect to beta, what we get if we do the first derivative is we obtain this expression on the top, and if we do the second derivative, we observe this. It is important here that X has a full column rank, so that simply means that X transpose X, which is our observed set of variables, is a positive definite. And in that particular case, if this is the case, if we have a full rank, then we can tell that the RSS, the least square or the loss function has a unique minimum, which is when the first derivative vanishes, when we make this first derivative equal to 0. If X is not full rank, unfortunately, we are not going to be able to claim that there is only one global minimum. But let's consider for now that X has full rank. We will look at problems of non-full rank in the next lecture, but not today. And then in the particular case of the multivariate case, basically what we are going to obtain is that our beta vector can be obtained as this, let me see, as basically X transpose X minus 1, the inverse of X transpose X times Y. Because basically I'm saying that my predictions are X beta hat, and if I remove the first X, basically I get all the thing on the right side. And this is basically, we put also the univariate case so that you can compare. I guess I just realized that in this expression, in solving for beta yields, basically beta hat, there should be an equal B between beta hat X transpose minus 1 XY. Otherwise, this doesn't make any sense. And whenever we want to make a new prediction whenever we want to make the predictions for all of our x's, everything that we need to do is multiply beforehand by x, and x beta hat is going to give us our predictions y hat. So what does it mean visually? Basically, if you could plot in the case of where you have two-dimensional inputs, and here on the y-axis we have the sales, so let's imagine that here we have the TV and the radio, and we put how every pair of x1 and x2 gives to a y. These are the red circles. Basically, what we are gonna be finding when we solve the least square solution that we saw before is actually a hyperplane that tries to be as close as possible on average to all these points. That is why you see this hyperplane having points on above and on the top, because basically it is the one that minimizes the residual sum of squares. Another type of interpretation is where basically if we plot a particular value for the variable x1 and x2 and the exact value that we observe for xy, basically our prediction is not going to be anything else than the projection of the y vector into the plane that is formed by the x1 and x2 vectors. So coming back to the properties of this estimator, I just want to recall that basically now we have solved exactly the same problem as we were solving before, but instead of having only beta 0 and beta 1, we have as many beta p's as number of dimensions plus 1, right? Because there is the bias term. And for that, we now need to do a bit of linear algebra, but everything else remains the same. Almost everything else remains the same. And still, this estimator of the beta vector now, it is actually not of the beta vector, but of the y hat. It is actually an unbiased linear estimator. And among all the unbiased estimators, linear estimators is the one with the smallest variance, as we were discussing before. And actually, in order for that, you can prove it by keeping in mind the Gauss-Markov theorem. And this is something that you are going to be seeing next week in the tutorial, as it is some part of your assignments to show that among all the linear unbiased estimator, the least square is the one with minimum variance. So you are going to be playing around with that. But to give you a few hints before you go into by yourself or with the help of our amazing team of TAs and tutors, basically, it is important to remark that basically we got our beta hat vector, which is of this form that we saw here. We recall that the y, we are under the assumption that it is a linear dependence between the x, the true beta parameters, and plus some additive noise. And if we basically substitute in our beta hat estimator and our least square estimator of the regression parameter, the y, what we can do is to show that basically beta hat is no more than the true value of beta plus some term which depends on the input data, input of feature data, and the epsilon, the noise variable. And if now I take the expectation of this beta hat condition on x, basically I can show that the expected value of this conditional is actually beta. And even if I go beyond and I take the integral with respect any potential x matrix, where x is no more than your training data, you have put all your training x's into a matrix. And now I say, okay, what if I, instead of having this training data, I would have any other according to the probability distribution? So that is why we have this probability of x's. Basically, I get that the expected value of beta hat is beta. And this is exactly why we know that this estimator of beta is unbiased. Okay. So this is the first step. So now you saw that the estimator is unbiased, minimum variance, next week in the tutorial. So whenever we have fit the multivariate case, we saw that in the univariate, before coming back to the univariate, we saw that for each value of the input, we were ignoring any other features. And then we obtained that with different T statistics, we actually observed that the three, the TV, the radio, and the newspaper, they were all predictive for the sales. But now, if instead of training an independent linear regressor for each of these input variables, I train a multivariate regression model where I consider the TV, the radio, and the newspaper jointly as inputs to my regressor, what I actually obtain is that while the TV and the radio, they seem significantly, statistically significant, this is not the case with the newspaper anymore, because basically I get a p-value which is very, very high. That means that given that I have information on the radio budget and on the TV budget, it seems irrelevant to use the newspaper also to make predictions on the sales. And the question that some of you may wonder here is why this is the case, right? And in order to answer that, the first thing that we can look at is actually at the correlation matrix between the TV, the radio, and the newspaper and the sales. And of course, the correlation of every variable with each other is 1. That is why we have a diagonal of 1s here. But if we look at the correlation between the TV and the radio, it is quite small. But if we look at the correlation between the newspaper and the radio, it is of 0.35. So this might indicate that all the information that the radio contains about the sales is already contained, all the information that the newspaper contains about the sales, it might be already implicitly accounted in the radio. And something that you can think is, in general, there might be a correlation. Maybe the people that were doing radio advertisement, they were also doing newspaper advertisement. This explains why the correlation. And we might be seeing some sort of spurious correlation that kind of before in the univariate linear model was telling us that, yeah, maybe if you invest in the newspaper, you will increase the sales. But that doesn't need to be the case, because it seems that the newspaper is no more than a surrogate of the radio. That basically people were investing jointly in both of them, And this is why we had this correlation. But if now we look at the radio newspapers and sales jointly, we can see that maybe the newspaper is not that important anymore. So in order to give you some examples, and I guess we are not gonna enter very much into the discussion in this course, but it is something that probably many of you have heard, is that actually correlation is not the same as causation. So you can see correlations between variables, but these correlations doesn't need to come from a direct influence, for example, of newspapers in the sales, but it might be due to some sort of confounder. And this confounder might be, in our example, the case in which maybe everybody that was investing in the radio was jointly investing in the newspaper, so it was not possible to separate the two effects together in our data. Or if we think of other cases, so you can think there's always this example of correlated inputs between the number of storks and the number of birds, but I don't think that the number of storks by any means causes the number of birds. This is something that some people commented, and apparently there are also some studies that correlate the number of gas stations in your neighborhood with the number of divorces, but I don't see any direct relationship with that. So basically, in all these cases, there might be a hidden confounder or a hidden effect that we don't get to observe, but everything that we observe is the correlation between these two variables. But because of this hidden confounder, we are not able to disentangle whether there is a causation between the budget in the newspaper and the sales, or it is simply a fact of some hidden confounders that we didn't account for in the data. So far, everything that we wanted to say in the multivariate case, just to summarize, is that even if you have observed some dependence or some statistical significance when you take one variable in isolation with respect to the target variable, that doesn't mean that when you consider more input variables in the data, that variable remains statistical significance anymore, because maybe all the information, as we were seeing of the newspaper about the sales, was already correlated with the newspaper, with the radio. So the questions that now we might wonder is actually which one of the input features, which in the book are called predictors. I'm still trying to familiarize with this notation. I'm reading this book together with you guys. Basically, when can we claim that an input variable, a predictor, is actually useful for the target variable that we might have, or if we have observed or we have measured a set of input variables, which subset of them might be useful to keep in our model? How well do we fit the data when we consider all of them or a subset? And how accurately we can predict the response, the output variable, depending on the subset that we select. So in order to consider hypothesis testing similar to the ones that we were doing when we did the univariate model, but now we have not only one input variable, but we have as many, the first question that we might wonder is whether this relationship that we saw between all of our inputs and our output are statistically significant. But now, of course, we don't have to consider only that one beta 1 is 0, but we might want to consider that our null hypothesis that all the betas associated with an input random variable are equal to 0. And the alternative hypothesis in this particular case would be that some of them, or at least one of them, is non-zero, that there is some actual information here. So in the multiple regression or in multivariate regression, instead of using the T statistic, what we are gonna instead use is what it is called the F statistic, which is no more than a different relationship between the the total sum of squares and the residual sum of squares, and also it accounts for the number of p, the number of input variables that we have, and also it accounts for the number of data points that we get. So basically, this is another way of another statistic that in this case allow us to see how well our model is fitting the data and whether the betas that we are getting actually are statistically significant or just happen by chance. So some remarks about this F statistic and the two different terms, numerator and denominator, is that it is important to remark that when the linear assumption is correct, and by meaning the linear assumption, I mean that the underlying relationship between the x's and the y is actually linear, of the form that we were saying before. Actually, the denominator is gonna know more, is gonna take the value, the expected value of the denominator is gonna be directly the variance of the y, or the variance of the error, because it is the same. And if H0 is true, that means our null hypothesis is true, which means all the betas that are related to an input random variable are equal to 0, then the numerator would be also sigma squared. And that means that we would have numerator and denominator sigma squared, so the F statistic will take value 1. If the H0 is not true, then what we will expect, what we will have in expectation for the numerator is that the value is going to be greater than sigma squared, and therefore the F statistic is going to be greater than sigma squared, than 1. So in general, the F statistic is going to have also some sort of shape. We can plot it, the probability density of the F statistic. This is how it distributes, and the particular shape of the F statistic is going to depend on how many samples you get in your training data, and also how many dimensions you get as input. And here you have some examples about how it changes when I change N and P. The F statistic, it is important to remark that in our case it's only going to be useful when N is greater than P. Because if we get more dimensions than training observations than N, our regression problem is going to be ill-posed, and we are not going to be able to tell, we don't have a unique solution anymore, and we are not going to be able to tell how well our estimator is. But if this is not the case, in general, the F statistic is going to tell us how well our model fit the data, or whether anything that we fit is by random chance. This would be accepting the hypothesis 0. So this is again the case, and you can measure the F statistic, and as we were doing before with the T statistic, we can say, okay, we accept or reject the null hypothesis with a p-value, with a confidence of the p-value. And this might be one way of using the F statistic, but maybe if we might be interested, instead of checking whether I want to do all in or all out, we might be interested in seeing which of the input variables I might be useful to use in this particular case. So instead of assuming that your null hypothesis is to put all the beta values to 0, all the beta values for all the variables to 0, you can decide to put only a subset of them to 0. So in our particular example, one might consider whether it might be a good idea to actually drop the newspaper as input variable, as it seems not to be adding too much. So in this particular case, what we can do is to compute the F statistic. And in this particular case, what we are going to have in the numerator is going to be the difference between the residual sum of squares when we consider all the variables, including the newspaper, with the residual sum of squares, which we call 0, when you put to 0 all these variables that you might be thinking of dropping, which in our case might be the newspaper. And here basically you have a division by Q, because basically Q are the the remaining number of parameters that you are gonna keep in the regressor. Okay. So in this particular case, we can continue. So, and there are two, in principle, it is not a very good idea to simply remove a variable based on the t-statistic of this individual variable by itself, but better to perform an f-statistic where you simply decide to check how the residual sum of the squares change when I consider these variables and when I don't. And why is that the case? Well, this is the case mostly because when I have a high dimensional situation, if I look at the t-statistics, in general, I'm gonna have very small values of p-values. And because it is not agnostic to the number of variables. While if you think of the f-statistic, we are already accounting for how many dimensions we are keeping or dropping. And this is already keeping in mind how many you have. And you are not gonna have the problem of having high dimensional inputs. So this basically summarizes what I just mentioned, and simply to remark that in general, when you are in the multivariate case, don't use the t-statistic to remove individual variables, but go into the f-statistic because it accounts for how many variables you have. Second point, only think of doing that when your number of dimensions is smaller than the number of observations. Because as I was saying before, if the number of observations is smaller than the number of dimensions, then you cannot guarantee that you have a unique minimum of the least square loss because you have more parameters than observations. So the problem in general, it is ill-posed. And we are gonna go into more details later on in chapter 6 of the book. But for now, remember that everything that we consider for the least square multivariate case, logistic linear regression, we were assuming that X is full rank. Our matrix of observations versus the input features is full rank, and also that P is smaller than N. If you are outside this particular constraint setting, you might not be doing that well. So the question that how do we, given that we have a lot of P's, right? How do we select what variables we want to use in order to make predictions? And for that, we can think of selecting important variables. But the problem that we may have is that we can think that if we have 3 variables, like we had, TV, newspaper, and radio, we can consider not having any of them. We can consider every pair of 2. We can consider the 3 of them. So basically, the number of potential subset of variables is gonna grow exponentially with the number of dimensions. And this is, I'm not sure whether you wanna really run as many statistical tests as potential subsets. So in that case, we are gonna see next in the last few minutes some approaches in which you can do this selection without needing to go over all these options. So if there are more details in the book, but basically here we are gonna simply discuss a couple of them. The forward selection, where we basically start with a model without any input variable. We only consider this Bayer or intercept term. And then we keep adding and compare basically how much we increase, or how we increase the fitting of the data, how much we reduce our RSS as we add more variable. And then we keep adding one by one until we fulfill some stopping criteria. And of course, we need to decide what the stopping criteria is. So this is not as easy, but there are some literature that enter there, and there is a bit of more discussion in the book. So if you are interested, have a look to that. And you can be in the other way around. So you can start with the backward selection and start with a full model where you consider train a linear regression with all your variables and keep dropping them by using this F statistic that we were discussing before, where you see, okay, how much my null hypothesis would be, what if I remove that compared to having all of them? And you can be changing your subsets until, again, some stopping criteria. I believe that in the book, they also discuss a mixed combination of the two. And depending on what is your number of P and how many observations you get, you can go for one, the other, of a mix of the two. So this is what basically the mix does. So basically you first do the adding part until the next adding variable remains insignificant, and then you try to remove some of the ones that you added. So you first go forward and then backwards. That answers how significant our input variables are and how to select a subset of them that might be interesting. But we didn't answer the question that we answered before on the univariate case about how well are we actually solving the problem that we want to solve, how well are we predicting. Why? And in this particular case, as I recall from before, we can again use the R-squared statistic. But in the case of the multivariate case, the R-squared statistic doesn't correspond anymore with the correlation between our input univariate variable and y hat, our predictor, to the square, but instead it is measuring the correlation between the true output variable, the true target variable, and our prediction of it. And basically, we have some examples here where basically we can show how the RSE changes when we have the full model with respect to the model that only accounts for the radio and the TV and you also see the F statistic and the R square. And basically, oops, my apologies. Basically, you can see that adding the radio compared to only having the TV seems to do a quite better job. You can see that in the R square. But when we consider the full model, when we add the newspaper, we are not getting much out of it. So something that it is important here is that basically the R square is gonna always increase when we add variables, because you are increasing the correlation. You can keep adding variables and you can keep increasing this correlation, even if they are weakly associated with the output. So in order to really make a decision on what variables to keep, it is gonna not be enough to only look at the training error, which is what we have been measuring so far, but we are also gonna need to look at the test error. Meantime, while we don't have test error, what you can do is also to inspect the data and see whether there is any particular relationship between your errors and the model, how the errors behave. So in case of how accurately we can predict the outcomes, in order to, instead of only looking at the residual sum of the squares, what you can also do is to measure confidence estimates on the output and also prediction intervals on the output. And basically, if we think of confidence estimates, in our case, we can measure it like the mean square error. We have these expressions here on the bottom. This is only advanced material that you can find in this reference that we give you here, but I believe also in the elements of statistical machine learning, not that much in the ISLR book. And basically, what we can find is that in general, the confidence intervals are gonna be narrower than the prediction intervals, because while one of them is accounting only for the reducible error, the former one is, the second one is also accounting for the reducible error. And the reducible error is also telling you that your prediction might be a bit farther away than you believe, mostly because when we look only at the reducible error, we are comparing, in the case of linear model, our estimator of the fx hat versus fx, while when we look at the prediction interval, we are also looking at the irreducible error of it that might tell you how off you can be in your prediction. So if we look at our example of the advertisement data, basically you can see that with 90% confidence interval, your sales are gonna be in this interval. But if then I also account for the prediction interval or reducible error, then I can see that these intervals spread a bit farther away than the former one. And of course, you want to know how well you are going to be doing. So in general, the second one is going to tell you how the sales are going to behave. And the first one has more to do about how much of your reducible error you can still fix. And with that, I think I'm basically 2 minutes too late, but I'm happy to answer some questions if you have any.